Good afternoon. My name is Kesavan and I work in this institute. So I wanted to talk to you about conic sections and more generally about the general equation of second degree. So what are the conic sections? You teach the circle, ellipse, parabola, hyperbola. So why are they called conic sections? Okay, so a section means you are cutting across something. So you cut a cone parallel to the base, you will get a circle. If you cut it in a slightly slight angle, you will get an ellipse. And if you cut it parallel to the slant height, then you will get a parabola. If you cut it, say, at a steeper angle, say even vertical, then you get you can even show it to children by means of a torch. If you shine it on the wall, by tilting the torch, you can get all these curves in the shadow. Okay, so most of you have seen, or probably you teach regularly, in its standard forms. So if it's an ellipse, then it's x squared by a squared plus y squared by b squared equals 1. Parabola with a minus sign in the middle, hyperbola, and a parabola is y squared equals 4ax or something like that. So what happens to these equations when the center is moved somewhere else or when the axes are tilted? After all, so how does the equation look like, and how do you recognize whether it's an ellipse or a parabola or a hyperbola and so on? So these are the questions which you would like to answer. The way, I don't know, you also must have studied it in college. The way I was taught is to turn the coordinate axes first. So you get a tan theta which you can compute, and from which you calculate sine and cosine, and then you make the transformation x dash equals x cos theta plus y sin theta and so on and so forth, and then you change the coordinate axis. It's some horrendous calculations which run to several pages, and this was in my days a full 10-mark question in the BSc analytic geometry paper. Okay, but actually if you use some linear algebra, the whole thing becomes very transparent. And also if you look at the old textbooks, there are lots of gaps. There are many cases which they don't cover, which sometimes they get away saying that these are imaginary lines or imaginary ellipses and so on and so forth. Actually they are talking of something else. So if you use some linear algebra, it makes it very clear, very transparent. And also it's nice because it shows the unity in mathematics. You see, you don't learn subjects in compartments, but actually each subject draws a lot from the other subjects. So let me start with some linear algebra and then see how we can apply this to the study of conics. So let me take a 2 by 2 matrix which is symmetric, real and symmetric. So I want to compute its eigenvalues. So we write down the characteristic equation. So what is that? Determinant of a minus lambda h b minus lambda equal to 0, and that if you write it, you are going to get lambda square minus lambda times a plus b plus ab minus h square. As you, I am sure, would have taught your students, for a 2 by 2 matrix, you don't have to laboriously write the determinant and compute it. To write down the characteristic equation of a 2 by 2 matrix is immediate. You just write lambda square minus lambda times the sum of the diagonal elements plus the determinant. Okay, so that will always give you the characteristic equation. So this is a quadratic equation, and if you look at the discriminant, that is a plus b the whole square minus 4ab plus 4h square, which turns out to be a minus b the whole square plus 4h square. So this is the sum of two squares, so it is always non-negative. So we have already found that for a symmetric matrix, the eigenvalues are going to be real or will always be real. It won't be complex. Okay, and eigenvalues will be the same, coincident, if a equals b and h equals 0, because sum of two, this discriminant must be 0, and that can happen only when each of the terms itself is 0. So this is the only case when you get identical eigenvalues. So now let us take eigenvectors. So au equals lambda u, av equals mu v. Lambda and mu are the two eigenvalues of this matrix. So if you write U equals U1 U2, V equals V1 V2, let me take the dot product U dot V, which is U1 V1 plus U2 V2. So let us compute this dot product. So I will take lambda times U dot V is nothing but AU dot V. And if you expand that, you will get A of U1 V1 plus H times U1 V2 plus U2 V1 plus B of U2 V2. And this turns out to be also U inner product AV. You compute it again, it's the same. These are just calculations which, and that I can now write as mu times U dot V. So if lambda is not equal to mu, when can these two be equal? Only if U dot V is 0. So this implies that the eigenvalues are perpendicular to each other. So when you have distinct eigenvalues, then the eigenvalues will be perpendicular to each other. If you have the same eigenvalues, then it can occur only when A equals B and H equals 0. So the matrix is of the form lambda lambda 0 0, and any vector is an eigenvector, and therefore I can choose 1 0 and 0 1 as eigenvectors, and these are always perpendicular to each other. So the moral of the story is, for a real symmetric matrix, you have two real eigenvalues and you can choose eigenvectors. Eigenvectors will be perpendicular to each other. Okay? And I will further impose the condition, since I can multiply these eigenvectors by any constant and it will still be an eigenvector, I will divide by the length of the eigenvector to get unit vectors. So henceforth I will assume that U1 square plus U2 square equals 1, V1 square plus V2 square equals 1. I have normalized these eigenvectors so that I get it. Now let me define the matrix P as U1 U2. I put the first eigenvector in the first column and V1 V2 in the second column. And then what is P transpose? This is U1 U2 in the first row, V1 V2 in the second row. Okay? Then if you look at this condition, U1 square plus U2 square equals 1, V1 square plus V2 square equals 1, and U dot V equal to 0, that will tell you that PP transpose equals P transpose P equals the identity one. Just multiply and check, you will see it. Now so if I now take AU, A times P, this is what? A times U1 U2 V1 V2. This is A acting on this column vector U1 U2, but AU is lambda U. So this becomes lambda U1 lambda U2. Similarly, A acting on V1 V2 will give you mu U V1 mu V2. And this is equal to U1 U2 V1 V2 multiplied by the matrix lambda mu 0 0, which is P times lambda 0 0. So if I now multiply both sides by P transpose, I get P transpose AP is the diagonal matrix lambda mu, where the diagonal elements are just the eigenvalues of A, and the columns of P are nothing but the eigenvectors. This can also be written in the equivalent form because of the fact that P transpose P equals PP transpose is identity. They are inverses of each other, and therefore I can write this as P in this form. Very good. So we will remember all this and now go to second degree equations. So when you have two lines passing through the origin, ax plus by equal to 0, cx plus dy equal to 0. So when you multiply these equations together, you get something x square plus something xy plus something y square. Okay, so then we look at equations of this form: ax square plus 2hxy plus by square equal to 0. So now I am going to look at this in a slightly different way. This is nothing but xy Now I am going to use the fact that A can be written in this form. So that means xy p lambda 0 0 mu p transpose xy equal to 0. Now I am going to make a change of variable. X dash y dash is p transpose xy, or equivalently, which is the same as saying xy equals p times x dash y dash. So explicitly in terms of the eigenvectors, this becomes x dash equals u1x plus u2y, y dash equals v1x plus now if you look at this equation, what does it say? It says that x dash y dash in other words, lambda x dash square mu y dash square equals 0. So that equation has been simplified by this change of variable. So what we have actually done is, by computing the eigenvalues and eigenvectors, done all the tan theta, cos theta, sin theta calculations with painlessly. Finding these eigenvectors is very simple, as we will see in an example later on. Of course, lambda and mu cannot both be 0, because then the matrix will be 0. So yeah, thank you very much. Thank you. So lambda mu cannot be 0 0, because if that is so, then the fact that A can be written in the diagonal form will mean that the matrix A is 0, there is no equation at all. So this we do not have to look at. Now if lambda and mu are both greater than 0, this equation has only one solution, x dash equals 0, y dash equals 0. Because sum of two positive terms is 0, each thing is 0. So this means that the set, this equation, suppose set S is the set of all x, y, such that this equation is satisfied. Then S is just a singleton set 0, 0. If lambda is less than 0, mu is less than 0, same story. Because again it's sum of two negative terms which is 0, so each has to be 0. So this is 2. So if lambda is positive and mu is negative, or lambda is negative and mu is positive, then you get lambda x dash square equals minus mu y dash square, or x dash equals plus or minus mu by lambda y dash. So you get a pair of straight lines. Yeah? Root of. Thank you. No. So minus mu by lambda is positive, okay, plus or minus. Okay. Yeah, fine. So the two lines now are u1x, because x dash and y dash you have the expressions here. So u1x plus u2y equals plus root of minus mu by lambda times v1x plus v2y, and then u1x plus u2y equals minus root of minus mu. So these are the equations of the two lines which are represented by that single equation. So now if lambda equals 0 and mu not 0, or mu equals 0, lambda not equal to 0, then one of these two terms will disappear and you get a single line, either the x dash equals 0 or y dash equals 0. So only one line, that is u1x plus u2y equal to 0, or v1x plus v2y equal to 0. If here we have one sub case, if lambda plus mu is 0, then you can cancel the lambda on both sides. Lambda equals minus mu, so you get x dash square equals y dash square, which is x dash equals plus or minus y dash. You have a pair of perpendicular lines. So this entire blackboard can now be summarized in a single picture. So this is lambda and this is mu, the eigenvalues of that matrix. You have to omit the origin because that is not to be taken into consideration. So in this quadrant we have lambda greater than 0, mu greater than 0. Set consists of only one point. Similarly here also. This is lambda less than 0, mu less than 0. If it lies on any of these axes, you have one line. And here you have two lines. Here also you have two lines. And if it lies on this line lambda plus mu equal to 0, then you have perpendicular lines. So just computing the eigenvalues and eigenvectors of this matrix AHHB will instantaneously tell you from this picture what that set is going to represent. So now let us look at a variant of this. So S is equal to set of all xy such that ax square plus 2hxy plus by square equal to 1. As before, you compute the eigenvalues lambda and mu, which are real, compute the normalized eigenvectors, and make this change of variable. Exactly what I did a few minutes ago. We'll now convert the equation to lambda x dash square plus mu y dash square equal to 1. So now let's look at the various cases. First, if A equals B is positive and H equal to 0, then lambda will be equal to mu equals A equals B, and this equation is a circle. If A equals B less than 0, H equal to 0, this is the empty set. This can never be satisfied. Because lambda and mu are both negative, sum of two positive terms, negative terms equal to 1 can never take place. So then S is the empty set. Three. If lambda less than 0, mu less than 0, again we are in the same case as before. This equation can never be satisfied, so S will be empty. If lambda is bigger than 0 and mu is bigger than 0, then this equation is precisely x dash square by 1 by root lambda whole square plus y dash square 1 by root mu whole square equal to 1, and that is an ellipse. So the square roots of the reciprocals of the eigenvalues give you automatically the semi-axis of the ellipse. So semi-axis lengths are 1 over root lambda 1 and 1 over root lambda and 1 over root mu. What are the equations of the axes of the ellipse, major axis and minor axis? They are precisely u1x plus u2y equal to 0, v1x plus v2y equal to 0. So the eigenvector immediately gives you the direction, the lines, equations of the lines. So in fact, what is the area of this ellipse? It is pi root of lambda mu, for instance. So if lambda bigger than 0 and mu less than 0, or vice versa, then you get a, what do you get? Yeah? Hyperbola. You will get a hyperbola because one is positive, one is negative. So you get x squared by a squared minus y squared by b squared equals 1. So again the lengths of the semi-axis are 1 over mod root lambda, 1 over mod root mu, that's all. And the equations of the semi-axis of the major and minor axis are still the same. So semi-axis 1 over root of mod lambda, 1 over root of mod mu. I am putting a mod so because one of them is negative. So and equations of the axis are continue to be given by the eigenvectors. And if lambda plus mu equal to 0, then you will get x dash square minus y dash square equal to 1, which is x dash plus y dash equal into x dash minus y dash equal to 1, and that is the rectangular hyperbola. So instead of perpendicular lines you get a rectangular hyperbola. And finally, if you have, this is 5, this is 6, yeah? Any prop? Yeah. Lambda gets 1 over lambda, you know. Take the positive one. Oh, sorry. Oh, that was your problem. Excuse me. Let's say lambda positive, okay. Then finally, if lambda equal to 0 and mu not 0, or vice versa, so then you get either x dash square equals 1 by lambda or y dash square equals 1 by mu, depending on the situation. So you get a pair of lines, okay. So so you get either x dash square equals 1 by lambda or y dash square equals 1 by mu should be, of course, positive. That means u1x plus u2y equals plus or minus 1 by root lambda, or v1x plus v2y equals plus or minus 1 by root mu. So these will be the pair of lines which you get in these situations. So again, so let us summarize it in a diagram. this is lambda, this is mu. I avoid the origin. Now if lambda is less than or equal to 0 and mu is also less than or equal to 0, including that, then nothing comes out of it. So this is lambda less than or equal to 0, mu less than or equal to 0. So previously even here you got a pair of lines, but because of the presence of 1 on the right hand side, now these get omitted also. No, they can't. I put a circle around the origin to avoid it. Okay. If it's on this axis or on this axis, then you get a pair of lines. And here you have lambda positive, mu positive. You have an ellipse. And here lambda negative, mu positive, lambda positive, mu negative, you have a hyperbola. And if it's on this line, lambda plus mu equal to 0, you have a rectangular hyperbola. So all the cases are covered just by looking at the eigenvalues. And the eigenvectors immediately tell you what the axes or the lines are going to be. You just have to write down the two eigenvectors and that's done. Okay. So now this is everything centered at the origin. So now we would like to move the origin also. So now we have to do two things. One is to shift the origin and rotate the coordinate axis. Of course you can do it in either way. You can first rotate the coordinate axis, then shift the origin. You can first shift the origin and then rotate the coordinate axis. One will be more convenient in some cases, other will be more convenient in different cases. So we will see both examples here. So all that I've said in the last half an hour or so are summarized in these two pictures here. So remember always you have AH, HB and two eigenvalues which are real, lambda and mu, and corresponding to it two eigenvectors which are orthogonal and normal and therefore form an orthogonal matrix system. Okay. So now we look at the general equation of second degree. So ax square plus 2hxy plus by square. Now there are lower order terms. So suppose this represents a pair of straight lines, say Lx plus my plus n equal to 0, L dash x plus m dash y plus n dash equal to 0. So assume pair of straight lines, pair of intersecting straight lines. Then you can compare the coefficients, and if you took Lx plus my equal to 0, L dash x plus m dash y equal to 0. These are a pair of parallel lines intersecting at the origin. And you know the condition, if you compare the coefficients, LL dash will be A, MM dash will be B, L dash M plus M dash L will be L, 2H and so on and so forth. These lines will be parallel to those lines. Okay, it's a pair of lines parallel to the original lines but intersecting at the origin. If they are intersecting, obviously they are not parallel to each other. Okay, yeah. Okay, so in that case we already saw that one eigenvalue must be positive and one eigenvalue must be negative to get two intersecting lines at the origin. That means the determinant, which is the product of the eigenvalues, has to be negative. Okay, so this implies that first of all AB minus H square is less than 0. So if you get a pair of intersecting lines, a necessary condition is AB minus H square should be less than 0. Suppose alpha beta is the point of intersection of these lines. So let us shift the origin there. So let us take x equals capital X plus alpha, y equals capital Y plus beta, so that the origin point of intersection is now changed to the origin. So if you rewrite this equation in the new coordinates, you will get a capital X square plus 2h capital XY plus b capital Y square plus 2 times a alpha plus h beta plus g times x plus 2 times g alpha plus f beta, sorry, h alpha plus b beta plus f times y plus a alpha square plus 2h alpha beta plus b alpha square, b beta square. Okay, that's just calculation. You substitute for x and y, separate everything, you will get this. But what is alpha beta? It's a point of intersection, so it must lie on the curve. So this will be 0. Automatically. And further, since this is a pair of lines now intersecting at the origin, it cannot have any x or y term. So you will forcibly get a alpha plus h beta plus g equal to 0, g alpha, h alpha plus b beta plus f equal to 0. And now this is a pair of simultaneous equations in two unknowns alpha and beta, and because AB minus h square is strictly negative, this has a unique solution. So the point of intersection can be determined by solving these two equations. Now if you combine these two with this condition, you can rewrite this condition, go home and do it as exercise. It will also imply that g alpha plus f beta plus c equal to 0. Yeah. So what does this mean? That alpha beta 1 is a solution for these simultaneous three equations, homogeneous conditions. That means that determinant must be 0. So alpha, beta and 1, so this is a non-trivial solution, whatever may be alpha beta, 1 is always there. So this solves this homogeneous system, and that is possible only if AHG, HBF, GFC equal to 0. Let us call this delta because we are going to talk a lot about this. So let us call. So if this equation should represent a pair of intersecting lines, then this determinant must be 0 and AB minus h square must be less than 0. So now let us see if the converse is also true, whether this is a necessary and sufficient condition. Okay, so now we assume that delta is 0, so converse, and AB minus h square is less than 0. Well, again I will rewrite this equation in this way. I will now choose alpha beta to solve this equation. So choose alpha beta. One is true. So now what happens? If I multiply this column by alpha, multiply this column by beta, and add it to this column, then I will get AHG, HBF, A alpha plus H beta plus G, that is 0, G alpha plus F beta, B beta plus F, that is also 0, G alpha plus F beta plus C is what I will get. And I know that this determinant doesn't change, so this will also have to be 0. I expand by this column, this is not 0, and therefore this has to be 0. So it forces G alpha plus F beta plus C to be 0. Once all these three are 0, then all these terms disappear, and you get ax square plus 2hxy plus by square equal to 0. And we know that this represents a pair of straight lines which intersect each other. We have already seen that, because ab minus h square is less than 0. So implies pair of lines. And now what are the equations of those lines? It is u1 x dash capital X plus u2 capital Y equal to 0, v1 capital X plus v2 capital Y equal to 0. This is how we did it in the first case. But now substitute for capital X and capital Y from there. So you have u1 into x minus alpha plus u2 into y minus beta equal to 0, v1 into x minus alpha plus v2 into y minus beta equal to 0. So these are the equations of the two lines represented by that. So this is a necessary and sufficient condition for this to represent a pair of intersecting straight lines, that this delta should be 0 and ab minus h square must be negative. What happens if ab minus h square is positive and delta equals 0? Well, you can go through all these things once more, everything will work, and this equation will reduce to a capital X square plus 2h capital xy plus b capital Y square equal to 0. and this means because AB minus S square is positive, both the eigenvalues are going to be positive, and you know that this represents only xy equal to 0 0. This is the only point. So in other words, xy equals alpha beta is the only possible solution to this equation. No other point satisfies this. So the solution set or this curve reduces to a single point, namely alpha beta, which you can solve for by getting these two equations. Now let us consider the case when delta is not 0. So then it can't be a pair of straight lines. We know delta equals 0 is a necessary sufficient condition for it to be a pair of straight lines. So delta not equal to 0. So again we have to look at two cases, AB minus h square less than 0 and AB minus h square greater than 0. So once more we compute alpha beta such that these two equations are satisfied. You can always find a unique solution because AB minus h square is not 0. So this 2 by 2 system is non-singular. So there always exists a solution. So once you have found it and you translate the origin, then what do you get? Ax square plus 2hxy plus b is not 0, so this cannot be 0. Okay, so this is not equal to 0. So let us call this some capital C. So you have ax square plus 2hxy plus by square plus capital C equal to 0 with C not equal to 0. So you can divide throughout by C and you will tumble into the case equal to 1 as we did last time. Okay. So if you have lambda positive mu negative or lambda negative mu positive, so this will become lambda x dash square plus mu y dash square plus c equal to 0, or I will write it as equal to 1 by minus c of this equal to 1. So the relative signs won't change because both of them are multiplied by minus 1 by c, and therefore in this case you have a hyperbola. And rectangular hyperbola if lambda plus mu equal to 0. Lengths of the semi-axis are again 1 over root mod lambda, 1 over root mod mu, and what are the axes? Axes are u1 times x minus alpha plus u2 times y minus beta equal to 0, v1 times x minus alpha plus v2 times y minus beta. So these are the axes of the hyperbola. If lambda is greater than 0 and mu is greater than 0, then both of these are positive, then it entirely depends on the C. So depending on C, we either get empty set or ellipse. So let's do one example. After all, it's high time. So let us look at 5x square minus 6xy plus 5y square plus 22x minus 26y plus 29 . So A is 5, this is 2h, so h is minus 3, g is, this is 2g, so that is 11, then h, then b is 5, f, 2f is minus, so this is minus 13, then it's a symmetric matrix, and c is 29. And you can check that this determinant is not 0. So AB minus h square is 25 minus 9, which is 16, which is positive. So either both eigenvalues will be positive or both eigenvalues will be negative. Okay, so either you are going to get empty set or an ellipse. Okay. So let us look at the equation 5 alpha minus 3 beta plus 11 equal to 0 minus 3 alpha plus 5 beta minus 13 equal to 0. So this will give you the center of the ellipse. So you will get alpha equals minus 1, beta equals 2. So this is the, so now you will change your coordinates, x equals x plus alpha, y equals y plus beta, and then this becomes 5x square minus 6xy plus 5y square equals 8. Okay, g alpha plus f beta plus c will be minus 8, and therefore so this is a positive number here. So if I divide by 8, I will get equal to 1. So this is certainly going to give me an ellipse. So this is an ellipse, and center of the ellipse is at minus 1, 2. So now let us look at the eigenvalues and eigenvectors of this. Okay, dividing by 8 is painful for me, but since I am going to divide by 8 throughout, for the moment I will leave it as it is. So I will look just at 5 minus 3 minus 3, 5. At the end I will compute the eigenvalues of this matrix, divide them by 8, I will get the eigenvalues of the other matrix. When you multiply a matrix by a constant, the eigenvalues get multiplied by the same constant. So I don't have to painfully do division by 8 and calculate with the vulgar fractions and so on. So I'll do this. So your characteristic equation is lambda square minus 10 lambda plus 9 plus 16 equal to 0, and that gives you lambda minus 8 into lambda minus 2 equal to 0. So the eigenvalues are 8 and 2, but for the eigenvalues of this one I will have to divide them by 8. So lambda equals actually 1 by 8, no, not 1 by 8, 8 by 8 is 1, and mu equals 1 by 4. So what are the semi-axes? 1 over root of lambda, so that is 1, 1 over root of mu, that is 2. So the semi-axes of the ellipse are 1 and 2. Okay, fine. Now about the equations of the axis, I have to find the eigenvectors. Yeah, does it bother you that the second one is the it doesn't matter which one it is, okay. 1 over root lambda, 1 over root mu. In fact, area of this ellipse is 2 pi. Pi AB, so it is 2 pi. So now we have to look at the eigenvectors. For the eigenvectors, again this 8 doesn't play any role in this thing, so I will just look at the eigenvectors of this matrix. So lambda equals 8 and lambda equals 2, I must find the eigenvectors. So I must solve 5x minus 3y equals lambda times x, which is 8x, and minus 3x plus 5y equals 8y. This is the eigenvector corresponding to lambda. But of course this equation you don't have to worry about because it's the same as the previous equation, being a, so this gives me 3x equals minus 3y or x equals minus y. So eigenvector is 1 comma minus 1, let's say, but I want an eigenvector of length unity, so I have to divide by square root of 2, so I will write instead 1 by root 2 minus 1 by root 2. So corresponding to lambda equals 1, which corresponds to lambda equals 8, you get 1 by root 2 minus 1 by root 2. Corresponding to mu equals 1 by 4, which corresponds to lambda equals 2. So now I will get 5x minus 3y equals 2x, and I don't have to write the other equation because it will be the same. Minus 3x plus 5y equals 2y will be the same equation as this. Now you get 3x equals 3y or x equals y. So any two, so 1 comma 1 is an eigenvector. I want something of unit length, so 1 by root 2, 1 by root 2. So major axis, which comes from here, comes from this equation x equals y, okay. So capital X equals y, or small x plus 1 equals y minus 2, because minus 1 2 was the translation which you did. So this means x minus y plus 3 equal to 0. So this is the equation of the major axis. minor axis will be x equals minus y, which corresponds to the eigenvalue which gave 1, which corresponded to 8, which gave you this one, which is x equals minus y, and therefore you will get x plus 1 equals 2 minus y, or x plus y minus 1 equal to 0. So you got the entire ellipse sorted out for you. So you have the center of the ellipse, the length of the semi-axis, the equations of the axis, so you know how to draw this ellipse. Okay, fine. So this is the situation when AB minus h square is not 0, and if delta equals 0, then you got a pair of intersecting straight lines. If delta is not 0, then you got an ellipse or an empty set. Now what happens if AB minus h square equal to 0? In that case, I have run out of time now, so I won't do anything, I will just tell you what happens. So if AB minus h square equals 0 and delta equals 0, then you will get a pair of straight lines which are parallel or coincident or empty. There won't be any answer. So that set will either be empty or parallel or coincident. If AB minus h square equal to 0 and delta is not 0, then you will get a parabola. Now unfortunately I don't have the time to do it, but this time we will first rotate the axis and then translate. Okay, so that is the only thing which we have to do, but anyway those things can be easily formed. So thank you very much for your attention.